The specific sampling distribution of any statistic is going to depend on two key factors. The first is, what is the statistic that we're actually talking about? Are we dealing with a sample mean, a sample median, the sample variance? Every statistic is going to behave differently in terms of its sampling distribution. The other key ingredient is going to be the population distribution. So how are the data actually distributed in the population? And again, if our population is normally distributed, that's going to produce different sampling distributions for all of the statistics than if it's exponentially distributed or if it follows some other type of distribution. And so when we're thinking about what is the sampling distribution of some statistic, we need to be thinking about a specific statistic, but we also have to be thinking about a specific population distribution. So for instance, we might think about what is the sampling distribution of the sample mean for a normally distributed population. Now, to sort of summarize what we're going to cover today, if the population is normally distributed, then the sample mean is also going to be normally distributed. So if we have a normally distributed population, then looking at the sample mean, this is going to have a normally distributed sampling distribution. And so this result is quite nice, and it's quite a good place to begin thinking about how those factors of sampling, how those factors of the statistic, as well as the population distribution, influence our sampling distribution. So to formalize this result somewhat, we can think about taking a sample from a normally distributed population. So x1 to xn are all drawn from a normal distribution with a mean of mu and a variance of sigma squared. Okay? We can think about these as being drawn independent from one another. We're forming our sample in the way we would typically think about forming a sample, but where we're specifying in particular that the population that it's being drawn from follows a normal distribution. The sample mean in this case is given by 1 over n times the sum of all of the data points that we observe. This is our standard average. This is what we think about when we're talking about our sample mean. Okay? So we can calculate the sample mean given the set of data from the population that we're thinking about. And our question is, what is the sampling distribution? Every time we take a different sample, we're going to get a different sample mean. And so there's sampling variability that's going to influence the distribution of the sample mean. We want to know what is that distribution. In order to work it out, we can take this fact here as given. And so what this fact states is that if you have any single sample from a normal distribution, right? So if we take W1 up to Wn to be independent from normal distribution, then the sum of them is also going to be normally distributed. Okay? And so using this fact, what we can say is, well, our sample mean here is basically just a sum of independent normals, right? This piece of the box here, this has to be a normal distribution as well using this fact. And we don't have to worry about where this fact is coming from, but it is true that if you add up a bunch of normally distributed random variables, then you're going to get something that's still normally distributed. Now, it's also true, and this is used a whole lot more often, that if you multiply something by a normal distribution, then you're going to get a normally distributed random variable as well, right? If you take something that is normally distributed, so what we have in the red box here is normally distributed, and if you multiply that by some constant out front, so 1 over n is just some constant, then you still have a normal distribution. Right, and so that's the idea, is that when you add up a bunch of normals, it stays normal. If you multiply a normal by something, it stays normal. And so because of that, the sample mean, if you have normally distributed data, is simply the summation and then scaling of the sum of a bunch of normals, right? And so this is going to be normally distributed. And so because of that fact, we get that x bar has to be normally distributed. Okay? And so that's sort of the important result here, is that we get x bar follows a normal distribution. And we can think about the expected value and the variance of x bar. So note that these results are not specific to the normal distribution. The expected value of x bar is always mu. The variance of x bar is always sigma squared over n, right? But once we know that x bar follows a normal distribution, then what we can say is specifically x bar follows this normal distribution with a mean of mu and a variance of sigma squared over n. Okay? And this all stems from us being willing to assume that the population is normally distributed. If we're looking at the sample mean, our population is normally distributed, then the sample mean has a normal sampling distribution. We can take a look at some examples of how we might calculate these parameter values here. So in this first case, we're thinking about researchers who are studying individuals with type 2 diabetes, and in particular, we're thinking about them measuring something like the average blood sugar, for instance, blood glucose levels. And so we're going to say that this is a normally distributed quantity, right? So the measurement that they're taking is normally distributed with a mean of 120 milligrams per deciliter and a variance of 25. They take a sample of size 49. And so what can we do with this information? Well, the first thing to note is that because the population is normally distributed, we immediately know that X bar is also going to be normally distributed, right? And so we have to ask then, well, what parameters is it normally distributed with? So we need our mean and we need the variance. The mean is always the same thing as the population mean. So in our case here, we know that the mean is going to have to be 120 because the population has a mean of 120. For the variance, we take the population variance and we divide by the sample size. In this case, we're told that the population variance is 25. The sample size is 49, right? And so what we're saying is then, well, the sampling distribution of the sample mean here has to be normally distributed with a mean of 120 and a variance of 25 over 49, right? This is an application of that result that we had. And indeed, if we find the result here, that's exactly what we get. We can take a look at another example here. We have a political polling example. So they're trying to gauge the support for a particular candidate in a region, and we assume that the proportion who support the candidate is normally distributed. It has a mean of 0.45 and a variance of 0.2475. Sample of size 100 is taken. And so once again, we can ask ourselves, well, what's going on here? We want to know the sampling distribution of X bar. Okay, well, X bar is going to be normally distributed because we've assumed that in the population, we have a normal distribution, right? Because we're making this assumption right here that the proportion of people in the population is normally distributed, right? Because of that, then we get that this is going to be a normally distributed sample mean. Okay, so what are the parameters? Well, the parameters are going to be the sample mean has a mean that is given by the population's mean, which in our case is 0.45. And the variance is going to be the population variance divided by n. So in this case, the population variance is 0.2475. Divide that by n, which in this case is 100. Okay. And so here we have this result again. X bar is going to follow this specific normal distribution. If we fill in the result, we get exactly that. We look at one final example here. So agricultural researchers are studying the yields of some particular crop. The crop variety has yields that are normally distributed. The average yield is 22,000 pounds per acre with a standard deviation of 4,000 pounds. A sample is taken over 25 acres. So here we're going to have essentially the same process, but there's one thing we got to be careful about, right? So we know that X bar is going to be normally distributed because the population is normally distributed. We know that the mean is going to be 22,000 pounds because that's what the population mean is. So the only thing that's left for us is to work out what the variance is. And the only thing to be mindful here is that we're not told what the population variance is. We're told that the population standard deviation, so that sigma, is going to be given by 4,000. And so what we should find is that, well, sigma squared is then 4,000 squared. And so as a result, the variance of the sample mean should be 4,000 squared divided by 25. Okay. And so because of that, we just have to take that extra step here. And if we do that all and we fill it out, we find that X bar is normally distributed because it is the sample mean from a normal population, mean of 22,000, variance of 4,000 squared divided by 25, which gives us 800. Okay. So what is actually going on here? So in this graphic, we can think about this process of working out the sampling distribution of the sample mean. So on the left-hand side here, we have what is our population distribution. And in our case, this is going to be sort of that nice bell curve shape. It's going to be centered at 0, and it goes up to about -3 and +3. That's where most of the data are sitting here. Okay. Then what we have are, over here, two different sample means or two different sampling distributions for the sample means. The first is with sample sizes of 10. The second is with sample sizes of 100. And so the way that we're forming those graphics is we go to our population, we take out samples of size 10, we calculate the sample mean, and then we do this over and over and over and over again. And all of those repeats, that's what we're actually plotting when we're looking at this graphic right here. And then we do the same process, except instead of taking samples of size 10, we take samples of size 100, right? And so that's what we'd be looking at in this lower graph on the right side here. And so what we can see, first of all, is that the population, that looks normally distributed, right? It's this nice bell curve. And both sample means look like they have normally distributed sampling distributions as well, right? And so that sort of is the key result of today, is that if you have a normal population, then you have normally distributed sampling distributions. The other thing to note are the parameters of this distribution, right? And so we have that the population is centered at 0. And if we look over here, both of these sampling distributions are also centered at approximately 0, right? And so that makes sense. The mean from the population is the mean in the sampling distribution. So the last piece to think about is this variability, right? And so we can go from about -3 up to about +3. So when we take a sample of size 10, we should see that the variance is smaller, right? The variance is going to get smaller because the variance is going to be the population variance divided by 10. And indeed, you can see that we're going from about -1 to about +1 here, right? A little bit more perhaps. When we go up to 100, then you can see that we're going from about, say, -0.3 up to +0.3. Right? And so in this case, we actually do see that reduction in variance. So this whole graphic for n equals 100 sits between -0.3 and +0.3. And so if we were to put it here, right, all of these data points are going to be falling sort of in this range here, which means that we're going to have sort of a much taller looking bell curve like this, right? And then it's going to trail out. Whereas if we think about what's happening with the sample size of 10, right, well, then we're about between -1 and +1. And so perhaps we're sitting somewhere like here to here, right? And so then it's not going to be nearly as large as the blue, but we're still going to be sitting out like this, right? And so you can think that we are getting less variable. The graph is being less spread out over this, and we can notice that in the actual variability that we see here. But they all look normally distributed, and they're all centered on exactly the same point. So if you have a normal population, the sampling distribution is going to be normal as well. So this is sort of a very important result in a lot of ways, right? If you want to do statistical inference and you're willing to make the assumption about normally distributed populations, then immediately we know exactly how the sampling distribution is going to be for the sample mean. We know exactly how the sample mean is going to behave, and we can use that for inferential procedures, calculating probabilities or conducting inference. The only real limitation of this result is that it only works for normal populations. And so if you have data that are not normally distributed, then we're going to need to turn to other results in order to accommodate those data.